Hi everyone. Now that we've worked somewhat with imaginary or complex numbers, I want to show you something called a complex conjugate. We're going to use complex conjugate to simplify some division problems, to rationalize denominators, to clean things up quite a bit. So first of all, you need to know what a complex conjugate is. If I have a complex number, some real number plus bi, which is the standard form that I showed you, its conjugate would be a minus bi. It would just be the opposite sign. And this is really clear because when you multiply something by its conjugate, basically you get rid of the imaginary thing. Let me show you how it works with letters. Why not? If I FOIL this, okay, I get a squared, I get negative abi, I get positive abi, and I get negative b squared I squared. Do you see that? Okay, these are opposites, so they cancel each other out. So I have a squared, and remember I squared is just -1, isn't it? So this, instead of being negative b squared I squared, this I squared changes this to a positive, and this becomes a squared plus b squared. So we're going to use that to factor. But that's what a complex conjugate does. Let me show you how you would use them. Let's say you have this division problem. You have the complex number 9 plus 12i, and it is divided by 3i. How would you do that? You do not leave a denominator with an imaginary in the bottom. So what you're going to do is you're going to do kind of what I just did. You're going to multiply by the conjugate. This conjugate of positive 3i is negative 3i, because it's really 0 plus 3i, so 0 minus 3i, it's negative 3i. So this one, I'm going to multiply this by negative 3i. And that's legal as long as I do the same thing to the numerator. I also multiply it by negative 3i. Now what I'm doing is I'm just multiplying this by 1. But it's 1 in the form of negative 3i over negative 3i. So multiply the numerator straight across and the denominator straight across. You're going to have to distribute. So this becomes negative 27i, and this becomes negative 36i squared. This I squared is negative, so this becomes positive 36, right? I'll rewrite it down here. Positive 36 minus 27i. There's our numerator. Now, 3i times negative 3i is negative 9i squared. That simplifies to be positive 9. So my denominator is 9. When you look at this, basically this means 36 over 9 minus 27i over 9. And I can simplify that. 36 over 9 is 4. 27 over 9 is 3. So my final answer is 4 minus 3i. I have divided this by 3i, and I got 4 minus 3i. Here's another division problem. We have a complex number, 2 plus 3i, divided by the complex number 1 minus 4i. The way you do that is you take this denominator, think of it as rationalizing the denominator. I multiply this by its conjugate. The conjugate of 1 minus 4i is 1 plus 4i. Here's the conjugate, 1 plus 4i. And I'm multiplying by 1 because I'm multiplying the numerator and the denominator by the same thing. So in this case, I have to do what we worked on before. I need to FOIL my numerator. So I get 2 plus 8i plus 3i plus 12i squared. This becomes negative 12, and 2 minus 12 is negative 10 plus 11i, and there's my numerator. Okay, now let's FOIL the denominator. Because it is a conjugate, I have 1 times 1, so that's 1. So positive 4i and negative 4i are just going to cancel out. I'm not even going to bother to write them. I'm just going to write this, which is negative 16i squared, isn't it? Do you see that? Negative times a positive, 4 times 4, and I times I. This simplifies to be positive 16, so 1 plus 16 is 17, and I have finished. That's what it is. Now, if I write this in legit standard form, it should be negative 10 over 17 plus 11 over 17i. There it is in standard form. Just so that there's no confusion, if you see this and you're asked what is its conjugate, and you see this number is a negative, don't let that confuse you. This real part you don't change at all. The conjugate of this is negative 5 minus 3i. All you do is change this sign for its conjugate. Here's one for you to practice. 8 minus 7i over 8 plus 7i. If you want to pause and see if you can work that out, go through the steps I just did, and then restart it, and I'll walk through and you can test yourself and see how you did. Okay, you should have multiplied both of these by the conjugate of 8 plus 7i, which is 8 minus 7i. Then you FOIL the numerator. 64 minus 56i minus 56i plus 49i squared. Whew. Simplify that. This becomes negative 49. 64 minus 49 is 15, minus 113i is our numerator. The denominator is 64, minus 56i plus 56i just canceled out, minus 49i squared. So this becomes plus 49, so it's 64 plus 49, or 113 over 113. So I have 15 over 113 minus 1i. There we go. I stopped and looked because my book says this is 112, but I'm looking and it's 64 and, oh, because it's this. Oh, it is 112. Ah! You guys could have got candy. So this is 112. 56 and 56 is 112. So this becomes 112i over 113, or like that. There we go. Did you catch me earlier and think, oh no, what did I do wrong? Yeah, I did wrong. There you go. You guys earn a candy. Or another useful use of complex conjugates is now in factoring. Let's say I have this and I'm asked to factor it. So notice both of these terms, 2 is in both, so I'll factor out the 2. And I have 2x squared plus 16. Now notice this is a perfect square and this is a perfect square, but that's a plus. So before, we couldn't factor that. We can only factor it if it was a negative, and then it would have been x plus 4, x minus 4. But because we know about imaginary, now, even though it's a plus, we can factor it. So what we need to do then is add in those i's to change the sign. So this becomes 2, this is x plus 4i and x minus 4i. So that's what you do when it's a sum of 2 perfect squares instead of the difference of 2 perfect squares. Here's another check. To pause, write out your answer. Maybe you can do this in your head. What does this factor out to be? Okay, did you pause it and check? This should be, because the square root of 81 is 9, this should be x plus 9i, x minus 9i. By the way, it doesn't matter which you write first. You could have written x minus 9i times x plus 9i. It's all good, but that's your answer. Okay, now we're going to get to the heart of this, which is finding all the solutions for this quadratic, including imaginary solutions. Before if this If our discriminant was negative, we stopped because there is no negative square root, and we said there's no real solutions. But now we're going to find imaginary solutions. So we're going to plug this into the quadratic formula and see what happens when we have that negative discriminant. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So 4 times 2 times 5 is 40, so we have 9 minus 40, which is negative 31. So 3 plus or minus the square root of negative 31 over 4. Do you see that? How does the square root of 31 simplify? I'm sorry, the negative, square root of negative 31 simplify. You take that negative out and it becomes an I. So what you have is 3/4 plus or minus I square root of 31 over 4. That's what it is in standard form, the real number followed by the imaginary. You could write it this way. That's even more officially right. The problem is sometimes students do this and the I looks like it's inside that square root box, and I want to make sure you know that it's outside of it. So in any case, this is your answer. Let's try one more. X squared minus 4x plus 5 equals 0. This one looks relatively simple. So let's practice this one. Pause the video, work it through using the quadratic formula, and then come back and see how you did. Okay, I'll do this fairly quickly. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This is 16 minus 20, so that's negative 4. So I have 4 plus or minus the square root of negative 4 over 2. All right, this is, the square root of 4 is 2, and that negative is an I, so this is 4 plus or minus 2i over 2. I can reduce. So this becomes 2 plus or minus I. Definitely simplify. There's your final answer. 2 plus I and 2 minus I are your two solutions in this one. How did you do? Right, that's working with complex numbers, and once you get the feel of them, they're not very difficult at all. So have fun with this, and I'll see you next time.